So yeah, that's right. We talked about the naming system and how sometimes, like sometimes you'll say chloromethane and sometimes you'll say methyl something something. So benzene has two names. Sometimes it's something benzene, like chlorobenzene or nitrobenzene, where nitro is a new functional group that we've not seen before. Methyl benzene, also known as toluene, and well, we could go either way here, chloromethylbenzene, or we could say that was chlorophenyl methane, couldn't we? So that's the naming system where we say something something benzene, or we can go for phenyl as like a side chain on the edge of an important functional group or another chain of carbons. So we'll talk about amines. Actually, amines you can name in two different ways as well. You can say amino such and such, or you can say something something amine. So if you put a amine on a benzene ring, you've definitely got two ways to name it. So we could say phenyl amine, or we could actually say aminobenzene there. Just a special one there, phenol. I'll come to phenol in a moment, and phenyl ethanone. So ethanone, because you've got a carbonyl group with two carbons either side of it, so it's definitely a ketone. So it has to end -one, but I've only got two carbons in the main chain, so ethanone, and then a phenyl on the side of ethanone. So phenylethanone. And phenylethene is a bit more logical. So we've got an ethene molecule, and then there's a benzene ring on the side. So phenylethene. These are all in the topic booklet. Just a few to note. If you've got a carboxylic acid on a benzene ring, everybody would call that molecule benzoic acid out there in industry, but actually its preferred IUPAC name is benzene carboxylic acid, which makes no sense to me at all. I could get along with phenyl methanoic acid, but benzene carboxylic acid doesn't click with me at all. Anyway, that is actually what it's called. I will call it benzoic acid forever after. If we make benzoic acid into an ester, it becomes benzoate. So a molecule where the benzoic acid is the root of the ester with an ethyl group is ethyl benzoate. And hopefully it's logical that benzoic would become benzoate, just like ethanoic becomes ethanoate. And an OH just on the molecule, so phenyl alcohol gets contracted to phenol. I think might be one of the first aromatic compounds that was discovered. It was used a lot as an antiseptic in the 19th century. Notice, by the way, that all three of these structures, which I just pulled off Google Images, all show benzene with alternating single and double bonds, because that's how benzene's shown, right? It's not correct. It should be a circle, but you're going to see both. It doesn't mean that there's another structure out there which is cyclohexatriene, which behaves like, no. All benzene is just benzene, where the electrons are delocalized in the ring in a pi cloud. But you will see both structures drawn. I don't know why. Okay. Let's have a look at our last mechanism then, which is electrophilic substitution. I'm sure you're aware that the alkenes take part in electrophilic addition. Where's the arrow go? The first arrow? double bond. Yeah, that's right. It goes from the double bond because it's, remember the curly arrow is the movement of pair of electrons. Yeah, pair of electrons. Of course, you now know that the ethene molecule is a flat plane, and those electrons are sitting above and below the plane. So we have a sort of sausage of electrons there, and a sausage below the ethene, making up the double bonds. So that electrophile sitting there attracts those electrons away from above or below the plane of the molecule quite readily. So benzene does something similar, except that whereas alkene bonds are readily broken, benzene quite likes things the way they are, thanks, and it wants its double bonds back. So benzene does not readily take part in electrophilic addition reaction. It doesn't behave like a molecule with lots of alkene groups. It's a different functional group, really. Okay, so we're going to start off by introducing this new functional group, the NO2 group, just called the nitro group. So adding a nitro group is usually referred to as nitration. First of all, we have to make the electrophile, and the electrophile is made with a fairly potent mixture of concentrated sulfuric acid and concentrated nitric acid. It's not a mixture you want to spill. Definitely not on your trousers. It would be, would pretty much dissolve anything. If you do this, it's a strongly exothermic reaction, a lot of heat given out. You have to do the whole thing in an ice bath to stop it getting out of control. And what we find is that, well, one of these acids is stronger than the other. Which is the strongest? You know, we're putting sulfuric and HNO3 in the ring to slug it out. H2SO4 is definitely the strongest. So H2SO4 gives away its proton, as Bronsted-Lowry acids like to do, which means that HNO3 has to take it, okay, which it does. So we end up with a protonated acid, H2NO3+, which is not particularly stable, and the H2NO3+ then dissociates to make water and NO2+. So that gives us our electrophile, something positively charged. The mechanism is quite short. But it's important you get the details right, so I'm really going to focus in on those. So the first arrow comes from, the first curly arrow comes from yeah, from the benzene, specifically from the pi cloud of electrons, because that's our donut of electrons above and below the ring. Remember the kind of diagram from yesterday. Where's our donut? There it is. So we draw that curly arrow coming from the circle in the middle of the ring. Now, because we've taken electrons out of that ring, it's going to break the ring of delocalized electrons. So when I draw my next benzene ring, it's not quite going to have that circle going all the way around. the carbon that's being substituted at the moment has now got 4 bonds. It's got an H. Remember, all of the carbons in the benzene ring have a hydrogen on. And it's now got the NO2 as well, and it's got the 2 other carbons. So it's got 4 carbons attached. It's a fairly standard carbon in that respect. It's not positive or negative. But the ring has lost an electron, so that is positive. So I'll put the plus down there in a sort of weird looking smiley face. But the plus is in that arc of electrons, the remaining delocalized electrons, which now go from kind of carbon 2 down to carbon 6. Yeah. So draw your ring really carefully. AQA do mark for this. If your ring goes beyond those 2 carbons, that will be marked wrong. Similarly, if your ring doesn't extend around far enough, that will be marked wrong as well. So you need to make sure that it goes really from this carbon here, the arc rather than a ring now, isn't it? From this carbon here, the carbon 2, all the way around and stops at carbon 6. Okay. Well, as I said, benzene wants its electrons back. So we take the electrons from the carbon-hydrogen bond and stick them back in the ring, and that makes out nitrobenzene.
So, why has it come from the hydrogen bond? The benzene hydrogen bond rather than the benzene NO2 bond?
Well, if we did that, we'd just go back to this.
Is it why is it? Is it because the H bond, benzene H bond is weaker, or has it got nothing to do with it?
I don't know. I'll have to look up the data, but quite often the first step, we've done reaction kinetics. You know that the first step is the slow step, where we're trying to break bonds. It's also often a reversible step.
Okay.
And if you do an organic reaction, quite often you'll put it on for reflux and leave it for an hour, or you might even leave it overnight. Yeah, put it in the fume cupboard, put the lid down, leave a note for the cleaners, and just say, please leave my reaction. And you come in the morning, because you're waiting for those enough intermediates to form, which then make it to product, and that might take a while.
Nice.
Whereas inorganic reactions like acids and bases just react, don't they? You don't have to wait around for an acid to react with a base. It just happens. Okay, so some details that are always examined by AQA, and which were common areas for people to forget. You must state that it is both concentrated sulfuric acid and concentrated nitric acid. Must both be concentrated. You can do this reaction all in one go if you want. You could go from H2SO4 through to HSO4 minus NO2 plus and water if you want. That's okay. And then we've mentioned the all-important arc that you have to draw being in the right place, and the usual kind of curly arrow rules. The first curly arrow comes from the circle, the second curly arrow comes from the middle of the carbon-hydrogen bond. Just while we've got nitrobenzene in the room, let's get rid of that, we don't need those. sometimes they will try and make it a bit more interesting by putting something else in the ring for you. So maybe a methyl group. The mechanism's the same. We still come from the ring to attack the NO2. I'm going to just turn that frown upside down. Just going to go around there today. Okay, just to show that it can be the other way up. And then from there back into the ring. We've still got our CH3 group on top. Now we've got our NO2 on the bottom. If we were naming that, probably start from the main functional group, wouldn't we? We start from the nitro group, so that would be carbon 1 here, 2, 3, 4, so that would be 4-methyl nitrobenzene. So I mention this just because if you do this reaction of conch sulfuric and conch nitric acid and you keep it nice and cold, at about 5 degrees you'll get nitrobenzene. If you let it warm up a bit, then you can actually get 2 nitro groups on the ring, and if you have it even warmer, you can have 3 nitro groups on the ring. Strictly speaking, that should be O2N, shouldn't it? There we go. Which would be called
methyl 135 trinitrobenzene.
Lovely. Thank you. If I just tell you that this molecule here used to be called toluene, then what could I call this? Trinitrotoluene. Sounds familiar. Sorry, I can't spell. Toluene. There we go. It's TNT. It's high explosive. It's one which can go off if you drop it or shake it or hit it with something. So I don't suggest you do this reaction at home because you probably won't have a home when you've finished. Very small amounts of it go off with a very big bang. But that is how you make TNT, honest. Or you can get gunpowder from a creeper. Yeah, go on.
Did you say they tend to go off spontaneously or when ignited? Shaken. That makes
That's all you need to do. Yeah. If you dropped a test tube of TNT, that would be the last thing you ever did.
Good to know.
Okay, definitely on the list of don't do this at home, kids. The other electrophilic substitution you have to know is the Friedel-Crafts acylation. Who are Friedel and Craft? We don't know. There are a couple of dudes, probably had beards. I'm going to go with beards.
Probably some very awesome beards.
I've got to look them up now. So what was that? Charles Friedel. Is that on? No. Yeah, that's clear. From Strasbourg. And James Crafts. Ah, some top whiskers there. He's American. From Massachusetts. Okay. So, Messieurs Friedel and Crafts are responsible for giving us the acylation reaction. What is acylation? Can we remember that? Acylation, we've met up with that before. Oh, yes, we have. What was our acylation reaction that we saw in the last topic? What's our acylating agent of choice?
In this case, we could probably use ethanoic acid.
Ethanoic acid will work also.
Ethanoic anhydride.
Ethanoic anhydride or ethanol chloride. Okay, great. And what's the acyl group? What group does that add?
C double bond O, CR, CH3.
Yeah. Okay. So CH3CO is the bit that's added. That's our acyl group. Yeah. CH3 C double bond O. In this case, it's added that to ethanol. Okay, so like that reaction where we had ethanoyl chloride, we're going to use ethanoyl chloride again to make the electrophile. But we're going to use the Friedel-Crafts catalyst, which is aluminium chloride. Now, might not have thought about aluminium chloride before, but if you were to draw a sort of standard dot and cross diagram for aluminium chloride, what would you notice? You know, sort of standard GCSE style dot and cross diagram for aluminium chloride. What would you notice? Help me finish this, someone. Yeah?
Would there only be 6 electrons in the outer shell?
There's only 6 electrons in the outer shell. That's right. I've got a couple there, and a couple there, and a couple there. And obviously the chlorines have full outer shells all the way around. But aluminium itself only has 6 in its outer shell. What that means is if a chloride comes along, here's my chloride with a spare electron in its outer shell, then it's able to supply aluminium with the electrons it needs to complete its outer shell. So if it means that aluminium chloride is going to be very, very motivated to take a chloride off something else. So of course, if we take a chloride off there, take a Cl minus off, our acyl group is left, but it's actually the positively charged acyl group. It's called the acylium ion. I didn't mention, did I? NO2 plus is called the nitronium ion. I'm fairly sure AQA never test that. Anyway, that's what they're called. And then this thing here would be AlCl4 minus. Okay, that's it. That's a full positive charge on the carbon there, by the way, and it has to be on that carbon. It's not on the oxygen or the CH3. It's on that carbon. And now we can just play out electrophilic substitution reaction in exactly the same way as we did for NO2 plus. Along comes our electrophile. The electrons come from the ring and attack the electrophile. That gives us our very smiley intermediate. With a plus charge. Remember, the plus charge goes in the center of that arc there. And then the electrons from the carbon-hydrogen bond back into the ring to make benzene great again. There we go. I'll just say that.
Yes.
Oh dear. Okay.
That should be a disclaimer.
It'll go viral now and I'll be on the news tomorrow.
It's not really reflective of his views. We can assure you, internet.
Okay. All right. So we make that, which is called. What's that called? What's it called? What's that one called? What's it called? What's it called? Why are you? Phenyl. Ether. What kind of functional group is it? Phenyl ethanone. Remember, it's still a ketone. It's just a ketone with 2 carbons in the main chain. Phenyl ethanone. And I think that's kind of it. Oh, no, very important thing to say. One last little bit, it's quite important. The H is an H plus, and the H plus gets together with the AlCl4 minus, making HCl and AlCl3, which means that the aluminium chloride is regenerated, which means that it's a catalyst. Okay, now we're done.